Have you ever stopped to think about what your social media feed, the internet, and, I don't know, a subway map all have in common? It sounds like a trick question, but they all speak this kind of hidden language, a simple code of dots and lines that, well, it secretly runs our world. Today, we're going to learn that language, graph theory. I mean, really, they seem totally different, right? But these massive, super complex systems are all built on the exact same, and you'll see, surprisingly simple principle. So, to understand the secret language, we have to start with its alphabet. And you'll be relieved to hear it's an incredibly simple one. It's just dots and lines. At its absolute core, graph theory is all about this one definition. A graph is just a collection of finite vertices, which are, just dots, and finite edges, which are the lines connecting them. That's it. No, really, that is the heart of this entire field. And this right here? This is all it takes to make a graph. You've got a few points. Here they're labeled A, B, C, and D, and then you have some lines connecting them. It's really just a visual map of relationships. And you only need to know two key terms. The dots, those are called vertices. Think of them as the things, the objects, like people in a social network or websites on the internet. And the lines connecting them, those are called edges. They represent the relationships between those things. Okay, so now that we've got the basic anatomy down, let's take a little tour of what I like to call the graph zoo. Because just like in the animal kingdom, graphs come in all different species, and each one has its own unique rules and behaviors. So, on the left, we've got an undirected graph. The best way to think about this is that the edges are like a two-way street. The relationship goes both ways. But on the right, we have a directed graph. See those little arrows? Those edges are one-way streets. The relationship only flows in one direction, from a starting point to an end point. Graphs can also be sorted by their complexity. A simple graph is really neat and tidy. There are no loops that circle back to the same point, and no parallel edges. A multigraph, on the other hand, is a bit more flexible. It allows for multiple direct connections between the same 2 points. And here we've got the two absolute extremes of connectivity. On the left, that's a null graph. It has vertices, but 0 edges. It's basically a network with no connections at all. And on the right is its total opposite, a complete graph, where every single vertex is connected to every other vertex. We're talking maximum connectivity. So, we've met the different species of graphs in our little zoo. Now let's learn the language we use to actually measure and describe them. Okay, one of the most important ideas is the degree of a vertex. Now, it sounds all technical, but trust me, it's incredibly simple. It's just the total number of lines, or edges, connected to a single dot, or vertex. It's really just a measure of how connected that one point is to everything else. Let's make this real. Take a look at this graph. If we focus on vertex V2, we can just count the lines touching it. 1, 2, 3, 4, 5, 6. So its degree is 6. Now, look way over at V6. It's all by itself. It has no connections, so its degree is 0. Simple as that, right? And there are two other key terms that give us a bird's eye view of the whole graph. The order is just the total number of vertices, basically how many dots are in our network. And the size is the total count of edges, how many lines are there. Put them together, and these two numbers give you a really quick snapshot of the network's scale. All right, so far we've seen what a graph looks like when it's standing still, but the real power, the real magic, comes when we start moving through it. So let's shift from just describing it to actually traveling across the network. So there are different rules for how you can travel. A walk is the most basic. You can just wander around, revisit dots and lines as much as you feel like. A path is a bit more disciplined. You can't visit the same vertex twice. And a circuit, that's a special kind of trip that starts and ends at the very same spot, kind of like a round trip. This flowchart right here really helps it all click into place. Every journey starts as a walk. Now, if you decide not to go over the same edge twice, your walk becomes a trial. And if you also don't visit any vertex more than once, that trial becomes a path. And if your trial is a round trip, boom, it's a circuit. See how they all kind of build on each other? Okay, for our final section, we're going to pull back the curtain and reveal a really beautiful piece of hidden logic. It turns out there's a fundamental mathematical rule that governs every single graph we've looked at, and it is shockingly simple.
And here it is. It's called the handshaking theorem. And what it says is, if you add up the degree of every single vertex in a graph, that total sum will always be exactly equal to 2 times the number of edges. I know, it sounds a little abstract, so let's prove it. Okay, theory is great, but seeing it in action is way better. Let's apply the handshaking theorem to this example graph right here, step by step. First things first, we're going to add up the degree of every single vertex. So we've got 2 for A, 6 for B, 4 for C. And when we add all of those up, the grand total is 20. Okay, remember that number, 20.
So the sum of all the degrees is 20. Next, let's just count the total number of edges, the lines in the graph. There are 10 of them. And just like the theorem promised, 20 is exactly equal to 2 times 10. It works perfectly. And it makes sense, right? Because every single edge has to connect 2 vertices, so each edge contributes exactly 1 to the degree of 2 different points.
So why do these rules even matter? Well, because they help us build incredibly efficient structures. Take this, for example. It's a special type of graph called a tree. It's a graph with no loops or cycles. That simple rule makes it the absolute perfect, most efficient way to organize information, which is why it's the foundation for everything from your computer's file folders to how entire companies are structured. You see, the key takeaway here is this. Graph theory isn't just some abstract math. It's a new lens for seeing the world. It reveals the hidden architecture of connections that shape our lives. So the final question isn't for me, it's for you. Now that you speak the language of networks, what hidden connections will you discover?